Using heat of reaction in conversions. I remember heat is either Q or enthalpy delta H. I know conversions, I have that big old diagram and stuff. The enthalpy of a reaction, or heat of reaction, is often utilized in conversions as well as all the other stuff, molar mass, STP, mole ratios, balanced equations. Whew! This allows scientists to predict how much heat a reaction will release or absorb. Okay, release is exothermic, absorb is endothermic, when performed with a certain amount of chemical, so the amount matters. This can be very important for situations where energy is required, but too much energy could be a bad thing. For example, cars require very specific ratios of fuel to air in order to work properly. Too much, and the fuel either won't burn well or it won't provide the correct amount of power. Too much air, I guess? I don't know. Or too little air, whatever, I get the idea. So it matters how much there is to get the amount of energy. Enthalpy values are given for balanced chemical reactions. Again, that balanced seems important. So it seems like the first thing you should always do is balance the reaction. Remember, this means that the coefficients are the lowest whole number values possible. So lowest whole number, so no decimals, no fractions. The enthalpy value is always relative to the coefficient in the balanced equation. Let me read that again. The enthalpy value is relative to the coefficient in the balanced equation. Okay, I'm not exactly sure what that means. I know the coefficient matters. I'll have to look at the examples. Negative enthalpies indicate exothermic. I know that. And positive enthalpies are endothermic. Yeah, I know that. The sign's very important. Okay, great. Thanks. Okay, let's look at this. How much energy is required to decompose 83 grams of potassium iodide? So I'm looking for energy. So I'm looking for Q or delta H, I guess. And it's giving me 83 grams of potassium iodide. I know that's Ki. And K is plus, I is minus, so they're balanced. Okay, there's my formula. There's my delta H. So the delta H, how do they do this? Okay, first they go to moles. Makes sense. You always go to moles, I guess. So use the molar mass, you get 0.5 moles Ki. And then they're going to energy, which is kilojoules. And it's per 2 moles Ki. So they're taking this number, but it's per the coefficient. So I guess that's what they meant when they said relative to the coefficient. I guess that's what they meant. Because it's the enthalpy, but it's per that coefficient. So if it were per one of these, it would be half. Okay, so then they do the math and they find out that's how many kilojoules would be needed. Would be added, which I guess makes sense because this is positive, so this is endothermic. So you have to add energy to decompose this, which I guess makes sense. You add energy to break something apart. Decompose is break apart, right? All right, number 2, when 5 moles of calcium chloride dissolve, how much heat is released into the water? So again, we're looking for heat, and we're giving 5 moles of calcium chloride. Calcium chloride is CaCl, but there has to be 2 Cl's because this is minus, right? And calcium forms a 2+. Don't forget that. Alright, so there's the enthalpy, and notice this is exothermic, and they're doing 5 moles. Now it's per 1, but the coefficient's 1, and it's balanced, so I guess that's fine. And they find negative 69.5 kilojoules of energy is released into the water. Here it's positive, but they're saying it's released, which means it's exothermic. So I guess they can drop the negative. But I guess if they said something like this, if they said the heat of the reaction would be negative 69.5 kilojoules, that they would still need the negative sign because it's not specific about whether it's going out or in. But here they're saying it's released, so it's fine, I guess. How much heat is released into the water. It's kind of asking for an absolute value. Okay, watch this again if you need to. Make sure you're always putting it per the coefficient. And you could also go the other way. You could go from the heat to the chemicals. These equations didn't do that. All right, bye-bye. See you in class.